Right, thank you, Luis. Can everybody hear me? Yeah, okay, good. So thank you for that nice introduction. So yes, as a geophysicist and as a new NICO member, it is an honor really and also a pleasure for me to give this talk to an audience of scientists that are not dominantly Earth scientists, right? And vice versa. It is not every day at Northwestern that you get to hear a talk right, about the fascinating mysteries of the inaccessible depths of our own planet. And so therefore I decided, rather than giving you a geophysical case study, right, that has some really amazing findings that, you know, might have direct societal relevance on a timescale of thousands to millions of years, instead I would give you a sampling or a smorgasbord of various geophysical studies that have a common thread that is data science. Right, so for a lot of the research that I have done over my lifetime, you know, was informed by data, and sometimes tricky data, sometimes a lot of data, and sometimes old data no one had looked at, and that needed a better, you know, method to look at it. Anyway, so interestingly, all of these studies that I'm going to tell you about today, this sampling or smorgasbord, they are about a variety of different types of data. And all these different types of data happen to be represented in data from just one day of recordings at one particular seismic station of the Northwestern University Distributed Seismometers Network. Right? And so there's 4 segments of 6 hours of data here, right? And you could see some ridge variation with time, which is on the x-axis. And you can see on the y-axis that the Earth is constantly moving, right? In fact, the Earth is constantly talking to us. But the variation on the time axis is also present in frequencies. The bandwidth of this signal spans 4 orders of magnitude in frequency, right? And that is much more than the bandwidth of sound that we can hear, for example. But these frequencies, they are 10 to 1,000,000 times lower than what we can hear. And therefore, but we still might want to listen to the Earth because she's talking to us like constantly, right? And so what we can do is we can take the data from our seismometer, which is a sophisticated infrasound microphone that we couple to the solid Earth, right? We can take this data and pretend that it wasn't recorded over 6 hours, but instead it was recorded in a minute or so. And so we can listen to it. Right, so that high pitch was a little annoying, right? Yeah. And that high pitch, right, is this signal right here and that right here. And that is a signal from an industrial operation that was busy during this time window. This, in fact, spans a local time window from noon to 6 p.m., right, in Chicago or near Chicago. And so it's a busy time of the day. Normally we don't put seismometers in cities like this, right? We try to put them as far away from human activity as possible because we really just want to listen to what the signals generated by the Earth itself. But this one had other reasons for being where it was. But what we can do is we can filter out those high frequencies and look only at the low frequency signal, right? And then we're left with this. So this is a low-frequency signal that was buried in that high-pitched signal and those spikes that you saw earlier. So it's the exact same time period, just the low frequencies. Normally we don't see that much, but in this case we see a bunch of energy over here. And this is ground motion here in Illinois caused by seismic waves from an earthquake in Japan. Right? And this was on a day in July in 2014, and this happens regularly. So we can record earthquakes all around the world with our essentially infrasound sensors. When I was doing my PhD research, my dissertation, you know, I was lucky if I had, you know, a dozen or even fewer seismograms per earthquake to analyze for my dissertation. But then, the start of this century, right? Students had a lot more, and researchers had a lot more data available, like maybe a few hundred per earthquake. And now we're in a decade where we have thousands of seismograms per earthquake, right? So we're faced with a big data explosion, just like all of your fields probably have been experiencing as well. Yes? Why'd you have to scoop me? I was going to get to that. Yeah. No, thank you for the question. It's a really good question. So yes, Northwestern University, our researchers at Northwestern University, and that might have previously been elsewhere, but now are here, contributed a generous share of data, right, from various seismic sensor networks that were installed all over the world, in Africa, Northern Africa, Southern Africa, South America, Europe, North America, etc. To help do these investigations of the Earth's deep interior. And currently, Northwestern University, as Louis mentioned, is maintaining this Northwestern University distributed seismometers mini network, right? And we, since recently, have a student-run team that engages with the data recorded from these seismometers. Yeah. Oh. All right. So that was the same signal, but without a higher pitch. Okay? So this NUDS has these two professional seismometers, but also a couple of educational seismometers on campus that we use for outreach events. And so in the top, you could see that these educational seismometers record weather pressure, especially barometric pressure changes as well, right? Because, yes, they're educational. They're not as much shielded from the atmosphere as a professional seismometer would be. So we also get groups of kids in. These are kids from Nichols Middle School that came and jumped right next to the seismometer, right, to generate as big of a signal as they could. And they were pretty successful. And in the end, these were 3 grades of middle schoolers that jumped all at the same time, like right next to the sensor, right? And look what they accomplished, right? It's a big peak right here. But then if you look at this signal from an earthquake in Argentina, a mere magnitude 6.7, right? The other end of the world, or at least a quarter around the world, the peak is almost as big as what those middle schoolers did jumping right next to the seismometer, right? Which is a testament to how powerful earthquakes really are, right? And how much energy is being released by them. And then if you look at this signal right here, that was the 2011 earthquake in Virginia, right? That damaged the National Cathedral in Washington, D.C., where people tweeted about, where the tweets reached Chicago before the seismic waves did. So it was, and people were unprepared for this because normally you think of earthquakes as occurring in the West or in Alaska, not in Virginia, not near the capital. Anyway, this signal, this was recorded here in Chicago by our educational seismometer, and it far outstrips what this 3 grades of middle schoolers can do. Right? So very, very powerful. And this was only a magnitude 5.8 earthquake. Anyway, I digress. Right? So these are the professional data from that same time segment that we listened to before, except these are recorded in the Ryerson Conservation Area, which is just a half-hour drive from here. It's a public area that you can go to. You can also go to see the seismometer and jump nearby it, although it's better if you stay away. And this is what that sounds like. Right, same time segment, same earthquake. And this bottom trace is the low-pass version of it, right? And it's roughly the same size as here because there's not nearly as much high-frequency noise on this seismometer, it being in a forest preserve rather than near industrial operations, right? So it looks bigger as well. So this is the low-pass signal. Right, and this is, again, that's seismic waves from that same earthquake in Japan. Okay, so helping me maintain these seismic stations and analyzing the data, right? It's a large, group of students that have been here and that have come and gone. And so these are some of their names. They've been really, really helpful. Also, we've worked with the USGS, who has helped us, get these stations installed and also communicate the data back, to a server in near real time to this data center. And I'm still going to get to it. And IRIS, the Incorporated Research Institutions for Seismology, is basically the organization that facilitates the archival and distribution of open data, right, in seismology. So yes, all of this data is open, and I'm going to get to why. And EarthScope, one of these stations, this particular one has been part of EarthScope before we adopted it, right, we as in Northwestern. And then, we had cooperation from industry, townships, and the regional forest preserve to make this happen. But the studies I'm going to show use data from all around the world, not just from what was recorded locally. This is just, I thought this is of local interest to us, right? So, I haven't. Okay, I guess we have it twice now. Oh, wow. Keep going. Okay. So if you want to listen to more of this, right, you can do that. And at the same time, helping us do science. And so you can go to this online citizen science thing called zooniverse.org and look for this project called Earthquake Detective. We need your help or your family members' help, to help us identify different types of seismic signals simply by listening to them. So please make a note of this, and thank you for doing that. And this citizen science project was developed by students that are currently at Northwestern, right? Vivian Tang and Boris Rustler, and a group of IDEAS students. So the first study focuses in, right, on this part of the seismic signal that we just looked at. This was the low-pass version, right, of the first data from the first station I showed you. So the last segment from noon to 6 p.m., the low-pass version, and we look at this sharp onset of that signal that we associated with that earthquake in Japan. And so we can zoom in on it, and you can see really how sharp that arrival is of that first P wave. Right? You might remember from middle school that P waves are the first seismic wave that will arrive after an earthquake. They have a lot of energy, and they have high frequencies. So they peak sharply, and therefore it's relatively easy to pick when they actually exactly arrive. So we can read those arrival times from these graphs, from these seismograms that we have. We read the arrival times of the seismic waves. And then we basically subtract from that measured arrival time the predicted arrival time that is predicted based on the location of the earthquake. And that prediction is going to be pretty good because that earthquake location itself is derived from these arrival times, right? And this is why we have open data, because earthquakes typically occur on the edges of tectonic plates, right? And which is also on the edges of continents and therefore on the edges of countries. And if you want to locate something, right, your GPS receiver or something else, right, a gunshot or something, if you want to locate it, you better have data from all around it so you can get a precise location. And if you, as a country, are always on one side of an earthquake, you're not going to be able to locate it. So very long ago, globally, everyone decided, all seismologists decided to collaborate and share data globally, openly and globally, so that we can do better in locating and characterizing earthquakes, right, and be better at helping society to deal with those events. And so this availability of open data in seismology has really catalyzed geophysical research. It's been very important. And so we're really lucky that we have a really good data center and so on, and lots of data centers around the globe that all work together on this data. Anyway, so the paths taken by these P waves, yes, but then there's still a difference because, as you know, in any regression or any fitting, right, you get an earthquake location or a line, you're not going to fit your data exactly. There's always residuals that you're not going to fit. And these residuals carry information about varying variations, spatial variations in the Earth's internal structure, right? It's the Earth's internal elastic structure, the elastic moduli, right, material properties that determine how fast these seismic waves go. And so, therefore, they also determine what paths the seismic waves take using Snell's law. And you might think that, and then also the times are recorded follow Fermat's principle, which you might remember from your physics courses as being the shortest path, right? But if you really paid attention, it's the fastest path, right, that these waves will take. And so these curved paths seem like they're a roundabout way, but they are the fastest because these elastic properties, they increase, right? The elastic moduli get higher as you go deeper, and therefore waves can travel faster. And this happens because of the intense pressures and the increasing pressure with depth that exists within our planet. Okay, so the further away you are, and so if this earthquake is here and you have sensors there, right, then P waves that were recorded further away have traveled deeper inside the Earth. So if you get P waves measured at a range of distances from an earthquake, you also get some depth resolution of where they have been. And so what we can try to do then is to measure a lot of these P waves from lots of stations and lots of earthquakes, and then back project their delay times right along these ray paths and try to localize where did these delays originated, right? And material scientists among you or biomedical researchers among you might recognize this process as tomography. Right, you use this to image the insides of samples using X-rays, or the inside of a body, right, also using X-rays. For the Earth, X-rays don't go very far, so we use seismic waves, right, because they go all through the Earth. P waves are body waves; they'll radiate through the entire Earth, right? They won't stick to the surface. They don't focus into the core. They go everywhere. These are body waves. So we can basically make a three-dimensional map of the Earth's interior using these arrival times, just these arrival times of these first arriving waves. Okay, so here's an example of a bunch of data. They are aligned, right? So this distance effect has been taken out of them. And so they're aligned by their predicted arrival time based on the earthquake location. So you can see that they're still a little wobbly. And then when we take those delays, these wobbles, these differences with the predicted times, when we take that out of it, then they align very nicely like this. And then we have a set of measurements we can use to map spatial variations in these elastic properties that I talked about, which tell us something about what temperature the Earth's interior is at or what its composition is. And then so my former student, Chao-Ting Lu, made this nifty tool, right, where you can interact with these waves and align them in different ways, and you can deselect the ones that are noisy and things like that. So that's really nice. Yes?
The previous graph showed something.
100
kilometers.
Yes. It's 6,370 something, depending on if you're in the equator or the pole. Yeah.
So, yeah, kind of out.
For a distance of 40 degrees. If you go 90 degrees, they hit the core mantle boundary, which is halfway between the Earth's center and us. Yeah. And then if you go further out, you'll actually get a little bit of a shadow zone because there's a low velocities in the outer core because it's much denser, right? And it's liquid. And so that's why why waves go slower in the outer core, so you get a little bit of a shadow. You still get scattered waves there. And then if you go even further, you get P waves that have traveled through the core. Yeah.
So depending on now what the angular.
Exactly. Exactly. Right. And that's why we can do this in 3D, right? Because these waves, yeah, they go everywhere. Right. So here's an example, right? Oh, yeah. And so it sounds easy, right? You just measure these delay times. And, or like you do tomography in a hospital or your sample, right, at Argonne. There you have a perfect configuration, right? You can put your receivers and your emitters like all around your sample or your body, and you can, do some math, like do a radon transform or something, and boom, you have your image. Here, we can't really do that for a variety of reasons. Some are common to all of these problems, but some are unique to geophysics. So one, there's errors in the data, right? And I don't have time to go into what they are, but they could be timing errors, or the instrument could not be working properly. The communication can be a problem, right? There can be all kinds of weird things, and I've experienced a lot of them over the 30 years I've been working with this data. So you need to, do your exploratory data analysis to understand what these errors can be. Also, interestingly, some of these data, these residuals, they have non-normal distributions, right? So even before I started working on my PhD thesis, I was doing a master's thesis, and I collected over 2 million delay times to try and use to make a 3D map, right, of the Mediterranean region. And so then, and this is the density of these 2 million delay times as a function of this distance that we talked about earlier. And the delay time is on the y-axis, so every vertical line here is, or every vertical scan here is essentially a histogram, right, of delay times. And you can see that the mean of these histograms wobbles around a lot with distance. And there's also these weird branches right here that are the result of the fact that, silicates in the Earth's mantle actually undergo phase transitions that were not incorporated in the model that was predicting the delay times at the time. So, basically I had to correct for this non-normal distribution and come up with a better reference model and so on. But then, you can use these delay times. But there's another problem. There's uneven coverage, right? So here, for example, you see a rotated little map, and I'm going to show you a lot of these. And then with a line through it, and that line is basically where we make a pie slice, where we slice the Earth open virtually to look at, a thin section of the interior. And so some of you might recognize Greece here, the Peloponnesos, the Ital boot of Italy, Sicily, Sardinia, Corsica, etc. Right? And we're looking along in that direction along this line. And that's what this is right here. So here we go down to 1,800 kilometers. You can see the ray paths. Some of them, come in and out of the two-dimensional plane you're looking at. And so you can also only see the segments that are within the plane of the cross-section. And you see this uneven coverage, illustrated. There's lots of earthquakes here in the Aegean Sea. And so there's a lot of paths that look very similar, right, that go to the same stations from the same group of earthquakes in the same region. So, we have a bit of an overkill of data here, right, which is okay. We can deal with that. That's always good to have more data. But then we lack data completely, right, beneath the seas here, in these various seas of the Mediterranean. And so then we need to come up with solutions for that. Yeah.
There,
hopefully,
any way to get
Oh, that's a whole other talk. But yes, you can, right? Actually, okay, so when P waves hit the floor of an ocean, they can convert to sound waves that can travel through the water, right? And so if you have a seismometer at the bottom of an ocean, you can measure it, the P wave itself. If you have a seismometer within the ocean, then you can measure that pressure wave or sound wave that travels through the water. If you have a floating seismometer, say hydrophone, right? It's not a microphone, but a hydrophone. It just measures pressure variations, not the actual directional ground motion that a seismometer does. Then that hydrophone is basically going to measure wave action. And so, yeah, you wouldn't want to have a seismometer floating on the oceans, on top of them, but inside the oceans. That is actually being done right now. And that's an investment that's going on, yeah, to try and measure more of these P waves. So, yeah, good question. Okay, so we need to make decisions about what to do with these regions, right? And yes, we can all agree that we need to find the simplest solution that can explain these data. But what is simple to you might not be simple to me, right? Some of you might say, well, if we don't have data here, we should keep the structure here exactly the same as the model that we use to predict the data, the reference model. But some of you might say, no, if we find that the structure here and here and here, right, is interesting in one way or another, we want to assign the exact same structure to these regions that are in between those, right? And that then gets into, decisions and choices you need to make about regularizing this system that you want to solve. Right? So eventually, we can deal with all these problems and set up this, linear algebra equation with a matrix G that has the theory of wave propagation in it, and then this model which has the Earth's elasticity or structure parameters in it, and this data vector which has these residual delay times for these P waves in it. And so that might look easy to solve, right? How about the least square solution? And so, right, the system is ill-posed, right, because it's both underdetermined and overdetermined at the same time. and so we need to regularize, but, you might do it differently than I do, right? So you have to make these subjective choices in some ways, right? You can, regularize on the first derivative, or you can regularize this on the size of M, the elements in M. And G, like I said, has a theory, but so basically it has the length of these wave paths in it. And then M would have the inverse of the velocity in it. So if you multiply G with M, you get the time, right? And that needs to match the observed residual times that we have in D. So, but, you might try a least square solution, but you can't really, because this G is enormous and it's sparse. It's really huge, right? Remember the 2 million delay times? Now, and that was in the 80s. And so, and then we have, and so basically, no computer can actually invert this, or not even invert GTG, right? And so therefore, we have to find iterative solutions for this system, even though a least square solution in theory would be fine, but we have to find iterative solutions of the same kind that are used in nonlinear optimization and in machine learning. So we solved the system eventually for lateral heterogeneity, and here's a result of that. And so again, we're looking at the Mediterranean Sea, except this is the Black Sea, this is Turkey, here's Crete, there's Greece, this is the Aegean Sea. All these white dots are earthquakes. These white dots are earthquakes as well. We go down to 1,400 kilometers, and we see blue and red colors underneath here, and this blue color that keeps going and going and going, that is basically the lithosphere, right, or the rocks that were underneath an ocean, called the Tethys Ocean, that was between Africa and Europe, a long time ago. But it subducted. So that lithosphere, that oceanic lithosphere that was at the surface, like imagine, right, the floor of the Pacific Ocean or the Atlantic Ocean, imagine that convecting back into the Earth. And that's what you're seeing here. Based on the earthquakes, we knew that was happening, but we thought it would stop here. But instead, it went down here and then even further into the lower mantle, right? This black dashed line is the boundary between the upper and the lower mantle. And because there's a phase change, people thought that there was no mass transfer across this boundary. But there is. Also, you can see these low velocities here, and I'll come back to that later. But these are responsible, right? Oh, yeah, and these red and blue colors typically represent temperature, but there's also issues on composition in play. So there's lots of volcanism in Greece, and that relates to these low velocities here. So, but yes?
So that color is sort of an estimate.
Well, this is actually an estimate of the elasticity, but these variations in elasticity are a function of composition and temperature.
Dots, the white dots.
Yeah.
In the top one is.
Yes.
And on the other one is out.
Yes. Exactly. Exactly. Yes. So we're looking at two different projections of the same system. Yes.
What's the
in this case, it's a few hundred Kelvin or degrees Celsius. Yeah. So, right? We could use the P waves for this, but there's a lot more to a seismogram. There's all these other seismic waves that arrive as well. So we can, instead of looking at only the P wave, we can look at all of these waves here, the S wave and the surface waves that arrive from any earthquake. And so, and then you can low pass these waves, right? And then you have a whole wave train. And so what we can do is we can try and predict this wave train, right, based on, wave propagation principles. In fact, we do this by calculating the normal modes of the Earth, right? Like you would compute the modes of a guitar string or a drum or something, and then sum them up to create traveling waves, and then, get a seismogram for a particular station and earthquake combination, and then we can try to fit that to the observations. And so, but the surface waves, for example, they don't radiate in all directions like P waves kind of do. But they have very interesting radiation patterns. They radiate more strongly in some directions and less strongly in other directions. Right? This is how love waves radiate, and this is how Rayleigh waves radiate, but in different frequencies. Right? And so this visualization of and investigation of how surface waves radiate and which is needed for how you predict them, right? That was made by one of my current graduate students, Boris Rustler, who is here. So we tried. So then this way we can use more waves, right? And all these waves have traveled along a different path, so we get even more depth resolution. These surface waves travel along the surface, so you can actually cover these oceans that weren't covered before by just the P waves. And so, and we can just do more in general. So, for example, this is an observed and a synthetic waveform, right, or a predicted waveform before we started fitting, and this is after fitting. And here's a lot of these sort of waveforms after fitting. Right? So we can do really well as long as we low pass these waves enough. And then we get from all of these fits, this is a nonlinear process, nonlinear optimization process, but we then extract linear constraints by diagonalizing the Hessian and all that stuff. And that you might do in machine learning as well. Anyway, and then we get linear constraints, we extract them from here. And then these are paths that we used, for example, from earthquakes to stations. And this looks a little bit like the flyer, right? The network flyer that was used to announce these talks with all these lines between one place and another. Well, seismic waves, connect like that as well, right? And then these dots here are basically the nodes of the grid, at which we determine these elasticity perturbations. So, right, and these figures are taken from a study by a former graduate student, Emily Wolin. So, and then we get these models, right, of the 3D Earth's interior, and I won't, tell you everything that we discovered, because I can't. But, for example, but basically all these elasticity perturbations that we can map, right, they basically tell us things, and they about temperature and composition, and we can quantify, right, the hundreds of degrees, right, or the 1,000 degrees if you go elsewhere. And also changes in composition, for example, the weight percent of water or hydrogen that makes it down into the mantle and stays there and affects properties there. We can tell all that by interfacing with other disciplines, like mineral physics, for example, right? So this is the cover of a book I edited with my colleague Steve Jacobson on basically how to do that, right? How to quantify the effect of water on seismic observables. And so, here you can see a map of North America that was made by another former student, Heather Beadle. And all this blue stuff is kind of like that oceanic lithosphere we saw in the Mediterranean, except this is not from the Tethys Ocean, this is from the Farallon Ocean, which existed up to 200 million years ago at the Earth's surface. And that's when it started subducting. But, but here you could see these low velocities on the East Coast, right? And then if you make a cross-section bam, through here, you get this pie slice right here. So this is the U.S. East Coast. And here, all these lines against our wave paths. And so here you could see that Farallon plate all the way down to the core mantle boundary, or almost to the core mantle boundary, which is at the bottom here. This is halfway down to the Earth's center. And then you could see these low velocities are the same as here. And we don't see a heat source for them, right? So as an exception, we don't think that these low elastic properties, these lower elastic moduli, that they represent higher temperatures. We think that this represents hydrated mantle. Water that came down with this Farallon plate was released here on the top of the lower mantle and is affecting the upper mantle beneath the east coast. And this can lead to an upwelling that can weaken the lithosphere at the surface, break it, and cause a subduction zone on the east coast, causing earthquakes and volcanoes and whatnot, right? So if you are from there, make sure you move away before 10 million years from now. Yeah. Because it'll be a dangerous place. Okay. And so here's another example, right, of how we can use all of this mineral physics data. Right? Yeah.
That's the way. Water in the system, and at some point that.
Yes. Right? And so that's also what this illustrates here, right? So here we're looking at that process much shallower than 700 kilometers. Now we're looking at about 100 kilometers. And this is a cross-section through South America. And this is basically, this here is Bolivia, so you can maybe orient yourselves a little bit. And then this is Brazil. And so I just want you to look at this part here. These stations here are on top of the Andes. And then we have a thicker crust, and then these very low velocities here, which means it's very, very deformable mantle there. And it is that way, right? On top of this line of earthquakes, it marks the boundary between the subducting lithosphere, which is cool, and the overlying mantle, which is normal hot temperature, but because the mantle is normally hot, but it is extra, it's extra deformable. Right, it has a very low shear modulus because there's actual water in here that is lowering the solidus, creating partial melt. Right, so it's basically low velocity because of partial melt that basically then migrates upwards and gets spit out from volcanoes. And so, yes, that oceanic lithosphere, right, subducting and convecting back into the earth is the main reason for earthquakes and volcanoes, not the only reason. But it's a dominant reason for this. And we were able to figure out from these the measurements of shear modulus here, we were able to figure out exactly how much water was needed and how much melt is needed by working with mineral physics tables like this one, compiled by Fei Wang, who is also a student here at Northwestern. And then and Mei Feng helped me, image, the mantle beneath South America, right? And this is just another perspective of the same thing. Right, so we've looked at the whole wave train, we've looked at the P wave, and now we're looking at scattered waves. So all these other waves we looked at are mostly direct waves because they are dominating seismograms. But there's also minuscule waves in seismograms that are scattered waves. The P wave, for example, right, can hit the boundary between the crust and the mantle and basically partially convert parts of its energy to another type of wave, like an S wave or something. And we can measure those S waves by doing a bunch of signal processing, right? So we can, find a way to represent the incoming P wave field and then deconvolve it from the wave field that should have these scattered S waves in it. And then we can stack them to enhance the signal and reduce the noise. And so this is an example of how that happens. And the fact that you see these gray bars, which represent the standard deviation, is because this is the result of many signals that were stacked together, right? And so anything that is rising above this gray area of 95% confidence, that is significant, right? Which is this blue peak here. This is the one we're interested in, which happens roughly 5 seconds after the direct P wave arrives. And this is a converted S wave from the boundary between the mantle and the crust. So we can not just map these sort of smooth changes in shear modulus or deformability, but we can also map where boundaries are by looking at the scattered waves. Right? And so we can do that, for example, near home in the Mid-Continent Rift, right, which is near Wisconsin and Minnesota and Ontario. And it's this kind of structure right here. The blue stations on this map are inside, on top of this rift structure, right? So this is You can't see much when you're there, right? Because it's all covered by sediments. But this was an active rift, like the East African rift is today. This was like that 1 billion years ago, right? And so nothing much has happened, right, to our part of the continent here since 1 billion years ago. I don't know if you've realized that, but you picked a really stable, tectonically stable place to live. So congratulations. And so
Fresh water, quakes, fires.
no lava, right.
Chicago is the place to be.
Right. So these green stations are basically on typical sort of continental old lithosphere, but these blue stations are on top of this rift structure, which is still there, but it's not doing anything, which is actually kind of interesting. And so, you can look at the delay times, and they have similar distributions, except their means are subtly different, and so on and so forth. So there's something here. And by looking at these scattered waves, you can figure out, maybe figure out what that is. And we think we did, right? Because this is from a green station. You see this nice scattered wave from the boundary, but here we don't see it. So where did the boundary go? Is there no boundary between the crust and the mantle? We see the crust from the surface, but where did the mantle go? It must be there, right? And so basically, we can look at, for a single station, look at all the earthquakes that were recorded, right? And this is pre-stacking. So this is the stack here, and this is all the individual ones. You can see that all of them have this scattered wave. This is the station that was not on top of this rift structure, but away from it. But this is the station on top of the rift structure. And you can see the scattered wave, but it comes in a little too early, as if it's a little shallower. And only from one perspective. The other perspective, the other half of the earthquakes, don't see it at all. They're coming in at a different angle, right? These waves were coming in at a little bit of an angle. So basically, we infer that the boundary is like tilted. And in fact, we, by looking at a lot of these things, right, we figured out that the boundary is actually splitting into two different boundaries. And so there's a lot going on here, but this is the boundary we're looking at, right? It's pretty good over here, but here it seems to be splitting up, and here also. So these are two cross sections here and here across the rift, right? This is a similar map as we saw before, except now the colors indicate elevated gravity, right? So if you're from there and you weigh more, that's because gravity is higher over there, right? But not by much, not something that your bathroom scale can detect, actually. So, but that was a joke. Yeah. But anyway, this gravity is higher, is elevated, because there are dense lava flows buried just beneath the surface from that billion-year-old rift. And so what we're seeing here at the crust mantle boundary, 40 kilometers deep, is that there's another lava flow right here that is hidden from the surface. But that is right here. And we think that this could be at least partially responsible for that subtle difference in P-wave arrival times that we've measured, over the rift versus away from the rift. So it's interesting that this thing that causing the gravity high over here, right, it has a counterpart below the crust. So, as if that wasn't enough, right, P-waves, entire wave trains, scattered waves, we're also looking at noise now. Data that wasn't signals, right? Because the noise is always going on, as you've heard. And so what we can do is we can take this sort of steady state, diffuse noise field, and if we look at enough of it, right, we can recombine it and tease out the waves that happen to travel from one station to another, right? So we can do that by okay, first of all, this is a noise spectrum right here, right, for a typical seismic station. This is one of those stations I talked to you about before, right? This SM23 was in the same region. And this is a period, which is the inverse of frequency. And you can see in these blue lines what the noise spectrum is, right? We're only going to look at this one, this vertical component one, not at these horizontal ones. These horizontal ones are very high here at these long periods because there's a correlation with barometric pressure, because in that part of the world we couldn't bury the stations deep enough because of groundwater issues. The stations would flood and the instruments don't like to be wet, and so we had to bury them more shallowly, and therefore they're more sensitive to atmospheric pressure. So that's this correlation right here, and that's also why this is high right here. But The vertical component is pretty good, except you can see this weird shape, right? Some frequencies are very strongly represented. So these are because oceans are never still. They're always in motions. And so this peak increases in the winter and lowers in the summer. And then here, this is our human activity right here, right? That pitch that we heard in the beginning is like way up here. But was at a different station it was. And then here we have a nice low noise floor. If you look at this noise spectrum for the one and only seismometer that we have on Mars, right, since last year, the noise floor is really, really low on Mars, right? Because there's no oceans, barely an atmosphere. It's very well shielded from the atmosphere. And yeah, there's no humans on Mars, so there's a very low noise floor. Anyway, so we can recombine all this. So we can get a Green's function between two sensors. Oh yeah, and because of this variation here, we need to normalize and equalize, right? We need to normalize to take care of the time variation and equalize to take care of this frequency variation. So because we don't want to dominate, and we want to look at all frequencies. So we can then get the Green's function by deconvolving the signal at one station from that at another station. But that's really hard to do with noise because you'll end up blowing up noise. So we approximate a deconvolution by a cross correlation. And we do that in segments day by day until we have a year of data that represents that nice diffuse noise field. So here's an example for one station. So if you go from one station to the other, you get a slightly different signal than going from the other station to the one station. But their arrival times of the different frequency components are roughly similar, and we could still use that data. And this is basically a lot of these type of records together, so you can really see how these waves move out as the distance between the stations increases. So we can map group velocities that depend on frequency and then turn them into shear modulus maps that depend on depth. Right? So this is near the boundary between the crust and the mantle, and it looks very much like this group velocity map for periods of 30 seconds, whereas the group velocity map for periods of 10 seconds, shorter periods, looks more like the upper 5 kilometers of shear modulus structure in this region. What is interesting, this is East Asia, by the way. So what we also did with this three-dimensional model, right, that we know there's a lot more variation and a lot more depth that I'm showing. But we can look at the vertical models or at these dispersion curves right here, and we can cluster them, right? And so basically, if we choose a cutoff level here of this cluster diagram, so we have 8 clusters in total, and then these are the clusters. It's interesting that all of these clusters are spatially coherent, or mostly spatially coherent, right? Indeed, indicating that, this is what geological maps look like. And the maps that we've made of the Earth's interior, right, they look have smoother variations. But now we're able to make a geological map of the Earth's interior, at least the upper part, the lithosphere of it. And so with just these 8 clusters, if we assign the mean model to each of these 8 clusters, to every point in these clusters, then calculate, and then repredict the data, we predict the data equally well as when we use that three-dimensional smooth model that I showed you in the previous slide. Right? So that is actually pretty interesting that the lithosphere clusters like that. So, as if that wasn't enough, we can do joint inversions of all of those things at the same time, right? P waves, scattered waves, entire wave trains, and noise. I will not go into that because I'm running out of time. So, there's a lot of other students involved in this. Well, and then finally, we can try and model all of it at once, like not in separate ways and then recombine them, but we can do a finite spectral element simulation of the wave field in a three-dimensional Earth, right? And that's ongoing research that is in progress right now that we're working on in South America with a visiting grad student, and again with Caillou, and also with Boris again. And so here's a snapshot, right, of some early iterations, and we need Quest to do this kind of numerical simulations of the whole wave field for this. And so, and these are the stations, a lot more than in that model I showed you earlier, because South America is also undergoing a data revolution. Right, and then here we see 3 components and all of these windows and the whole wave train and everything all together. So it's a big operation. So knowledge of the Earth's interior structure, right, provides its key to the past, right? We can see the literature from these past oceans inside the Earth. It also gives us a snapshot of the present. Where is it hot? Where is it wet? Right? And then we can think about how did it get to be that way? And what does this mean for other planets? Right? How do other planets evolve? Why did the Earth evolve the way it did? And some of these structures provide clues for the future, right? That hydrous upwelling on the North American East Coast, it could create a new zone of havoc on the East Coast with earthquakes and volcanoes and things like that. So by understanding this dynamics of the Earth's interior, right, we can maybe better predict the future on a time scale of millions of years. Yes. So last but not least, I want to ask this question. We've looked at a lot of this signal, but now, there's all these things, and what on earth are these, right? And if you've ever tried to get funding, you know it's very hard to get funding for a research question like that. But we're still trying to look at this in multiple different ways, right? Here's a close-up of one of these. It doesn't look like anything we know. So, we're kind of searching. And we're doing that on 4 different avenues, right? We continue maintaining our distributed seismometer network, with Igor Afrasio and Reese Elling and this new student team. This is a temporary name for it. And Mitch Barklage was helping previously. We're also trying numerical modeling. So if this is an earthquake, we can not only calculate how waves propagate away from it, and this is an example for surface waves, but we can also, model the stresses that propagate away with these surface waves, right? And these stresses, and these stresses in return can actually maybe trigger earthquakes themselves, right? It's not just tectonic stresses that can trigger earthquakes, but maybe stresses from seismic waves can also trigger earthquakes. And so here's a cross-section of stress from that Mexican earthquake on the San Andreas Fault, shear stress and normal stress. And this is calculations again by Boris Russler. And then my other student, Vivian Tang, worked with Prem Sitaraman and Brian Pardo and Kevin Chow and myself, to try and recognize more of these small, what on earth are these kind of events within data, but trying to run a machine learning model that can automatically detect and pick these out. Because we can't look at every 7 seconds of all these thousands of seismograms for years and years of data, That is impossible. So we're trying to find these using a machine learning algorithm. And then lastly, we're also using subspace methods, or have tried to use subspace methods, until our funding ran out. And so, which is, I also don't have time to explain right now, but it's very nifty. So, in conclusion, unraveling the dynamics of the solid Earth requires that we have data, observation, but lots of data science, the right methods to analyze them, but also ways to better predict the data. And then we can make 3D maps of the Earth's interior structure, which didn't tell us about the temperature and the composition, but tell us about the evolution of the Earth and what it all means and what might happen in the future and so on. We want to understand the Earth's interior for the same reason that you might want to understand the universe. And so, but you need to also interact with other disciplines, which is why I'm really happy to be a part of NICO and IDEAS and other programs here in the university. Thank you.